Okay, our next segment on fluid statics is the concept of the buoyancy force. And I like to write buoyancy force as BF. I don't know if everybody else does it, but I like it. So we're going to find the buoyancy force on an object placed or submerged inside the liquid. So here it is. There's a container, some liquid in it. We push a block down into that liquid, and that block is going to experience a buoyancy force. Means there's a buoyancy force means it's a force that buoys up or pushes up an object that's submerged. Now, if the buoyancy force is greater than the weight of the block, it will get pushed up and it'll float. If the buoyancy force is less than the weight of the block will simply sink to the bottom, although that buoyancy force will always be there. The question is, how big is it? How do we calculate it? And the way that's done is by looking at the pressure at the top of the block, which is caused by not the pressure, but the force at the top of the block, which is caused by the pressure at the top of the block. And then there's a force pushing back up from underneath because there's pressure at that location as well. And since the bottom of the block is deeper into the liquid, that means the pressure there is greater. And since the force is simply the pressure times the area, the force upward will be greater at the bottom of the block than the force downward at the top. In other words, the buoyancy force can simply be calculated by taking the force at the bottom and subtracting from that the force at the top. It's a difference between the force at the bottom and the force at the top on the block that will create that buoyancy force. And again, since the pressure is equal to the force divided by the area, which means that the force is equal to the pressure times the area, we can plug that in here, and you can write that the buoyancy force is equal to the force at the bottom, which means it's equal to the pressure at the bottom times the cross-sectional area, excuse me, minus the force at the top, which means the pressure at the top of the block times the cross-sectional area. So since the area would be the same for both the top and the bottom, we can simply say that it's equal to the pressure at the bottom minus the pressure at the top times the cross-sectional area. Okay, so what is the pressure at the bottom? Well, the pressure at the bottom can be found by pressure is equal to rho g y. Okay, so that means that this is equal to rho g y at the bottom of the cube minus the rho g y at the top of the cube times the cross-sectional area. So in either case, density is, of course, the density of the liquid, which is the same for both top and the bottom. G is a constant, so I can also take that outside the parentheses. So the buoyancy force now simply becomes equal to, let's say here we take the rho, the g, and the a all out, so that gives us y at the bottom minus y at the top times rho g n a, rho g n, the cross-sectional area. So what is the y at the bottom and the y at the top? Well, the y at the bottom would be the distance from the top of the liquid to the top of the cube, and added to that c, the height of the cube. I just call the height of the cube c. So this is equal to y plus c minus the height from, or the distance from the top of the liquid to the top of the cube, which is simply y times rho g times a. And of course, y plus c minus y, the y's cancel out, so this is equal to c times rho g times a. Now, a is the cross-sectional area of the cube, and c is the height of the cube. So c times a is really the volume of the cube, so this is equal to rho g times the volume of the cube. And now let's analyze this. Rho is the density of the liquid, g is acceleration due to gravity, and v is the volume of the cube. Now, density times volume. There's another equation that we have. We have the density, by definition, is mass divided by volume. So we can say that the mass is equal to the density times the volume. So that means that the density times the volume is equal to the mass of the liquid that was there before we put the cube in there. Remember, the density is not the density of the cube, it's the density of the liquid. So the density of the liquid times the volume equals the mass of the liquid that was there. So this is equal to, buoyancy force is equal to mass times g. And mass times g is actually the weight. So we can then say that the buoyancy force is equal to the weight And the weight of what? The weight of the liquid that was there before we put the cube in the water, which, in other words, is the weight of the liquid that was displaced by the cube. So the buoyancy force is equal to the weight of the displaced liquid. And that is known as the buoyancy force. Let me write that a little bit better because it's not written very well here. So the buoyancy force is equal to the weight of the displaced liquid. And that's the principle of the buoyancy force. So whenever you put an object inside a liquid, it will displace the liquid, and the force by which it's being buoyed up is simply equal to the weight of that liquid that was there before it got pushed out of the way by the object. Wow, that's interesting. So that means if the object weighs more than an equivalent amount of liquid, it will sink to the bottom, because then the weight of the cube is greater than the weight of the displaced liquid. But if the weight of the block is less than an equivalent volume of liquid, then the block will stay afloat, because then the buoyancy force is greater, because the weight of the displaced liquid is greater than the weight of the block, and so the block will then float. And that's how you find the buoyancy force of a cube. We're now going to use this principle of the buoyancy force to find the mass, to find the density and so forth of objects, and you'll see that in the next segment. Okay, that's it.